All right, guys, sorry for the delay. It's time to party. So Vir Bulchandani will be telling us about the classical limit of quantum max cut.
Hi, everyone. I'm a physicist at Rice University. It's really a pleasure to be here. I got hooked on this problem after attending a Simons workshop a few years ago. And I'm mostly going to try to convey why I got hooked on it. This is more of a survey talk on promising directions than actual results, but think of it as a statement of intent. Okay, so we've heard many talks in this workshop about the increasingly fruitful dialogue between computer science and physics. And this romance actually started a while ago in 1972 when hidden in the middle of Karp's reductions was this reduction to max cut, also known as finding the ground state of the classical Ising model. This can be trivially related to finding the ground state energy of the quantum Ising model, which leads to the eminently sensible idea of trying to do quantum annealing on programmable devices. And more broadly, we might hope that if we replace this classical ground state problem with a quantum ground state problem, we should get quantum complexity classes. And this was done initially by Kemp, Kitaev, and Regev, but it took about 2 decades of work to actually get to physically reasonable Hamiltonians here. So I'd particularly like to flag the work of Cubitt, Montanaro, and Piddock, who really bridged this gap between physical Hamiltonians and quantum complexity classes. And so taking this analogy seriously leads us to this pleasing statement that quantum ground states are officially hard to find. If you're a physicist and you've encountered the transverse field Ising model and the Heisenberg model, you know anecdotally that the solvable cases of the Ising model are much easier to treat using Jordan-Wigner fermions than the solvable cases of the Heisenberg model using the beta ansatz. So somehow this difference in hardness that computer scientists expect is even reflected in their exact solutions. So computer scientists know that these things are included within one another. It's consistent with our feelings. Any strict inclusion here would be huge, but sadly beyond reach for now. The concrete thing about this hardness for physicists is, as Chaitanya pointed out, it actually implies there are limits on how well we can even approximate these problems, let alone solve them exactly. So if we let lambda star denote the largest eigenvalue of our Hamiltonian, there is a limit on the approximation ratio that we can attain as defined in the red equation. And the classical PCP theorem says that that hard limit is at 94%. Many people believe that the hard limit is actually at 88%, pending the resolution of the unique games conjecture, but that's still a conjecture. So at a high level, this implies computational limits on the kinds of physical question we can hope to answer. Now, it's immediate from the statement that quantum problems inherit these classical limits. So if I just take my transverse field Ising model and set the fields to 0, I immediately get those classical PCP limits. So this is maybe not so exciting. Of course, we should understand these classical limits. We should understand how hard it is to solve quantum problems classically, but there are much richer possibilities out there. So I particularly like this recent framing by Lee and Barak, who just thought of optimization problems in terms of a prover and verifier, and just pointed out that there were multiple kinds of algorithm we could be considering in this space, and that people are mostly focusing on the algorithms, at least in this quantum max cut literature, where you are basically always operating in the classical world. And probably if there's a quantum advantage going to happen, it's on the QQ arrow rather than the CC arrow. But yeah, I just wanted to flag that we're looking on the top row, and it would be nice to get to the bottom row eventually. So in the rest of this talk, I'm going to motivate and describe the Caribbean-Barak algorithm for quantum max cut in more detail, and then present our generalization to higher spin and explain how you can see this as a bridge from QMA to NP. Okay, so how did we get from Germans-Williamson to Caribbean-Barak? So when you first look at this problem of computing the ground state energy of the quantum Heisenberg model, you can formulate it as a semi-definite program, but it's an intractable one. It's an exponentially complicated thing to solve, and a simpler thing you can try to do is optimize over two-point correlation. So this isn't exactly how the original algorithm was stated, but it's more of a streamlined statement. But then you can, if you just choose to optimize over matrices of two-point functions, you get a tractable SDP that you can solve in polynomial time. And this is a relaxation because not all of these correlation functions, of course, will come from physical density matrices. If I optimize over the space of two-point functions, not all of those will come from a density matrix. And you can think of this as the first level of a hierarchy closing in on the physical state space from the outside. You can extend it by including three-point functions, four-point functions, etc. One thing I want to flag is that there are many, many ways to do this. So this idea of studying physical systems from constraints imposed by physicality actually started in high-energy physics in the 60s with the Bootstrap program. So that has continued now for about 60 years in its own way, essentially solving physics problems through SDP relaxation. This literature doesn't seem to know about the quantum information literature on this problem until very recently. And similarly, there are efforts in quantum chemistry led by Mazziotti and collaborators and in condensed matter physics. I think that for some reason, these semi-definite programming relaxations have not been as useful in the condensed matter setting as they have been in high energy. I think that's partly a lack of awareness. They're simply not very well known in that context. But the point to emphasize here is there are many, many ways to construct relaxations. And in practice, there don't seem to be enormous advantages from considering one relaxation over the other. Right, so what I would say is the harder problem is the rounding problem. And the workhorse of condensed matter physics is so-called variational functions, wave functions, where you basically you guess a wave function to get an inner bound on the energy you're trying to compute. This is a hard problem in general. If you do a very good job of it, you might win a Nobel Prize. There are wave functions named after BCS and Laughlin because they captured enough of the physics in their trial wave function that they really changed our understanding of these systems. So you might be familiar with examples like Gaussian states, tensor network states, valence bond solids and liquids. These are all examples of variational wave functions. There are 2 points I want to make here. First, to actually optimize meaningfully over any space of variational wave functions, you need to be able to compute things. And I think this is a non-trivial requirement. There are actually very few complicated many-body wave functions where we know how to compute things exactly. This suggests some kind of interplay with quantum integrability that I don't think has really been explored. And this is related to the question of, so I cited many references, each of which proposes their own hierarchy of semi-definite relaxations on the last slide. Why don't we have analogous hierarchies of roundings? Why don't we have hierarchies of spatially non-local wave functions that work as well? Now, arguably, a tensor network state is an example of such a hierarchy, right? You can increase the bond dimension and interpolate between a local and a non-local regime, but I think there's nothing as standard as, say, these relaxations where you take two-point functions, three-point functions, and so on. Okay. So the best known algorithm for max cut is, of course, achieved by combining these two ideas. You first relax the problem to some easier semi-definite program, and then you round it into the set of feasible states. Now, I've formulated this as a quantum optimization problem, so you see that the physical state space is massive, but it just so happens that because it's secretly a classical problem, the optimum is tangential to the set of product states. So this is a sensible rounding procedure, which is why it does pretty well. We get this famous 87.8% approximation ratio. Now, Gharibian and Barek's proposal, decades later, is very similar. You're still rounding to a random product state. It's just that the optimum in Hilbert space is now very far from a product state, so you don't really know how well that approximation is going to do. But the idea is the same. So you take this Hamiltonian, you relax it in terms of its two-point functions, and you randomly round to a product of what physicists would call block coherent states. These have the nice property that if you take the expectation value of x, y, z, you get a genuine unit vector on the sphere. And that's it. These algorithms are very elegant in the sense you can just write them in a few lines. And raises the question of, is it any good? So it gets an approximation ratio of 49.8%, which is lousy in the scheme of things, but it's stunningly near optimality. It's actually a fraction of less than 1% off being optimal in the space of product states. So clearly it's capturing something important about this problem. I think my current record might be out of date, but as far as I know, it's 59.5%. And the wave functions that come up in this are reminiscent of things that arose in the strong disorder physics of random Heisenberg models in the 80s, so-called random singlet states. You can think of the Lee and Barek algorithm as basically a clever and computer science inflected way of constructing a random singlet state about which you can prove stuff. Now, the problem with these renormalization group physics approaches is you can't prove stuff. Even so, this is like reliably getting 59.5% of the ground state energy. And I think a challenge to all of us is to do provably better. In fact, we expect there to be limits on how well we can actually do. And to see these limits, you have to go to the limit of very high degree, or what you might call very high spatial dimension, where physicists are taught that mean field theory works. Now, this fact about high dimension was proved by Brandau and Hauer in 2013, and it lets you show that in this model, in this limit, quantum max cut actually reduces to a purely classical problem, so-called rank 3 max cut, where you really have a classical Heisenberg magnet that you're trying to optimize. And now this is a purely classical problem. It's in NP, and it's amenable to Gurman's Williamson rounding. Okay, and this classical problem has a known approximation ratio that Briette and collaborators worked out. It's around 96%, and it's believed to be the best you can do in the same way that 88% is the best you can do for ordinary max cut. So the upshot is that any quantum algorithm you can dream up for this problem will probably hit the 96% bottleneck. But the question I now want to raise is, what should we make of this bound? How seriously should we take it? It's a statement about the classical hardness of approximating some classical subset of instances of this problem. It's not really taking into account the extra hardness of entanglement, the fact that these optima are going to be entangled. So this work I'm about to describe was just motivated by this question of, how do we understand this mean field bottleneck? How seriously should we take it? And specifically, can we come up with problems where this scheme of Gharibian and Barek, rather than being 50% compared to the 96% theoretical limit, actually hits this 96% limit? So we're going to try to come up with a hard quantum problem where the Caribbean-Barack scheme is actually optimal or close to optimal. And this brings me to spin S quantum max cut. So if you're a physicist, there's a very natural way to tackle the problem I just posed. You go to highest spin. So rather than defining max cut in terms of Pauli operators, you define it in terms of spin operators. And this is normalized to match quantum max cut when S equals 1/2. As S goes to infinity, we know by results proved by Lieb in the 70s that this should recover rigorously a semi-classical limit. And intermediate values of S should be somewhere in between. Now, the crucial point here is that all of these problems have the same product state value. So if you use this high degree or mean field intuition, you will get the same bound for every single one of these problems for every single S, which is this 96%. So they all inherit this classical bound from the work of Huang and collaborators. And then we can ask, well, how close can we get? And again, if you know about semi-classical limits, you know that we're going to get arbitrarily close. So there is a traditional way of doing this as a physicist, which is you study the classical mean field theory, this limiting classical problem, max cut 3, and then you embed the classical state you get in the quantum Hilbert space as a product of block coherent states, just like the Caribbean-Barack rounding for spin 1/2, but now for any spin. And then Lieb's inequalities tell you essentially an automatic approximation ratio. So I realized that Bravi et al. Had also made this observation that Lieb's inequality can be viewed as an approximation ratio. They use the spin half case. Here we're using the higher spin versions of that statement. And what this lets you do is take your classical algorithm, embed it in a quantum state, and get an approximability guarantee. And in this case, it's just this prefactor, this spin-dependent prefactor times the 0.956. And for spin 1/2, it's much worse than Caribbean-Barack. And a natural question is whether it does better for any larger value of the spin. But to answer this, first I need to tell you how the Caribbean-Barack algorithm gets modified for larger spin. So using this rounding to block coherent states, which is defined for any qubit dimension, I can actually get a sequence of STP relaxations that interpolate between quantum max cut and classical max cut. So you actually have a sequence of relaxations that go from the quantum to the classical problem, and you can do the same rounding to all of them. So we have these two sequences of algorithms based on slightly different relaxations, but the same rounding rule. And now the question is, how do these two things compare? And remarkably, Caribbean and Barack beat Lieb's inequality for every single value of the spin S. So somehow, whatever they're doing knows about semi-classical limits. It seems to know about these non-trivial results on semi-classical approximation of quantum systems. Perhaps there's a better result out there. Also, both our algorithms converge to this same bound from below. For the blue line, it's trivial. We put that in by hand. For the red line, it's less trivial. It's a nice consistency check on our analysis that things are getting so close to that bound. And it is at least circumstantial evidence that that bound is robust. So for large S, these are now becoming pretty good algorithms. I think 96% is a respectable approximation ratio. And then there is the question of, can one do better? Can we extend some of these ideas on monogamy of entanglement at spin 1/2 to higher values of the spin? So that's an interesting question for the future, I think. Especially because it might suggest better things to do in the classical limit, optimistically. Why is this interesting from a computational complexity viewpoint? Well, we proved that this specific anti-ferromagnetic thing was QMA complete for all values of S. So you really have a sequence of QMA complete problems that are tending to something in NP. I don't know what this will be good for, but it seems like an interesting thing to have, basically a bridge from a quantum complexity class to a classical complexity class, and maybe some of you will have ideas about what to do with this. Okay, so let me just, in my final minute, let me close with some speculations. If quantum computers truly are more powerful, we might expect quantum optimization to be harder than classical optimization. We might expect the approximation ratios we get for these problems to be lower. That doesn't seem to be the case. Given the existence of these mean field regimes in hard quantum problems, maybe this isn't true. Second, semi-classical limits give a particular clean way to bridge quantum and classical complexity classes that I don't think has been explored at all and would be interesting to look at. The final thing I want to emphasize is that it seems to me that rounding is really the hard problem here that we don't really have a clue how to address. And I think this will require a concerted interdisciplinary effort because you need both physics and computer science to get something useful here, I'm guessing. Okay, so thank you for listening to my collaborator, Stephen Piddock at Royal Holloway, University of London. And there's the link to the paper. Thank you.
Okay, great. Thank you very much. We're running a bit late, so could then maybe the next speaker come up and set up in the meantime? And if there are any questions for Vir, we can probably take one or two until the next speaker.
Yeah, I had a question about, so for the rounding algorithm you gave, you rounded to coherent states. Is there a reason to believe or not to believe that rounding to non-coherent states could do better or worse?
There is a reason. So you can prove that in the space of product states, coherent states are optimal.
Okay, thank you.
So we did that.
Thanks for the great interdisciplinary talk and perspective. So I like what you said at the end about this, the semi-classical limit and trying to understand how you go from quantum to classical. Do you have any ideas for coming up with hard instances for quantum max cut, which has been really hard to do, through this perspective? I mean, I know you're looking at product states and coherent states, but do you have any thoughts on?
In a word, no, but let's discuss further maybe. Yeah, I'm not
Sure.
Thanks for the great talk. So you also argued that we should have a hierarchy of rounding, and you brought the example of tensor bond dimension. So in that case, wouldn't it be a problem if you increase the bond dimension that you might get stuck in local minima? So higher hierarchy, going to a higher hierarchy might not result to better result in rounding.
Well, at least, even if you're stuck in a local minimum, there's at least some guarantee that you'll converge as you increase so I think that's important, that there exists a better approximation with high, even if you're in a local minimum, somewhere you don't know about.
Okay, so thanks very much. Let's thank Vir again.